In this section, we're going to look at introduction to modern physics. Modern physics. Now, what we call modern physics is the physics developed after 1900s. Modern physics is physics developed after the 1900s, after, let's say, early 1900s. The physics before 1900s called classical physics. Physics before 1900s, is called classical physics. This is basically Newton's and Maxwell's physics. That is Newton's and Maxwell's physics. That is Newton's mechanics and Maxwell's electromagnetic theory. Okay, so what happened in 1900 to initiate the study of modern physics? Well, 3 experiments were done at the turn of the century, that in the late 1800s or early 1900s, that revolutionized physics. So we're going to look at these 3 experiments. Okay, in the late 1800s and early 1900s, 3 experiments were done that contradicted classical physics. Experiments were done that contradicted classical physics. These experiments were the Michelson-Morley experiment, Michelson-Morley experiment, the black body radiation experiment, black body radiation experiment, and the photoelectric experiment. Photoelectric experiment. So since these experiments contradicted the predictions of classical physics, then new theory has to be developed. Okay, so we're going to look at these experiments in the next sections. All right, we're going to start with Michelson-Morley experiment. Michelson-Morley. These are 2 American scientists. This experiment has to do with relative speed. For example, let's say you have a car, let's say going with speed v0, and then let's say you fire a bullet with a speed v. What would the speed of the bullet be? According to Galilean transformation, the speed of the bullet would be v0 plus v, okay? If the car is moving with a speed v and a bullet is fired from the car with a speed v, then the speed of the bullet would be v plus v0, okay? So the speed of the bullet would be the sum of the speed of the car plus the speed of the bullet with respect to the car. Okay, this is called Galilean transformations. It's theory developed by Galileo. Okay, now let's say this car is going the speed v0 and then it flashes light. What would the speed of the light be? According to Galilean transformation, the speed of the light will be v0 plus the speed of the light with respect to the car, which is c. Okay, So according to Gaussian transformation, the speed of the light emitted by the car would be the speed of the car plus the speed of the light. But this experiment, the Michelson-Morley experiment, found out that the speed of light is always a constant, that is 3 times 10 to the power of 8 meters per second, irrespective of the speed of the source. Okay? So, according to Galilean transformation, if a source moving with a speed v naught, let's say, the speed v naught, let's say, emits light, then the speed of the light is expected to be v naught plus the speed of light with respect to the sources producing the light, right? But the Michelson-Morley experiment found out that the speed of light is independent of the speed of the source. That's always c, irrespective of the speed of the source. But this experiment found out that the speed of light is always c, which is 3 times 10 to the power of 8 meters per second, independent of the speed of the source that produced it. Okay, so this was the produced the light. Okay, so this was a contradiction. Let's say you've got a car moving speed v naught, it produces light, then you'd expect the speed of the light to be the speed of the car plus the speed of light. But this experiment found out that the speed of light is always c, irrespective of the speed of light. So a new theory has to be developed to account for this new finding, and the scientist that came up with a new theory to explain this finding was Albert Einstein, which developed the theory called special theory of relativity. Okay, so to accommodate this new finding, Albert Einstein developed a new theory called special theory of relativity, special theory of relativity. Okay, this theory is based on the following two postulates. Okay, so the postulates of the theory are the following. The first one was the finding of the Michelson-Morley experiment. So the first postulate Einstein used is that the speed of light is always a constant, independent of the speed of the source. This is one of the postulates he uses, which is basically the finding of the Michelson-Morley experiment. And the second postulate is that all coordinate systems moving with a constant velocity with respect to each other are equivalent. All coordinate systems moving with constant velocity with respect to each other, velocity with respect to each other are equivalent. What this means is the formulas of physics will have the same form in all coordinate systems that are moving with constant speed with respect to each other. Okay, so Einstein developed a new theory called special-theory relativity to accommodate the finding of Michelson-Morley experiment, which states that the speed of light is always a constant independent of the speed of the source, contradicting the theory developed by Galileo. And the postulates he used to do that is, the first one is basically the finding of Michelson-Morley experiment, which says the speed of light is always a constant independent of the speed of the source. And the second postulate is that all coordinate systems moving with constant velocity with respect to each other are equivalent. So using these postulates, he came up with some conclusions that contradicted common sense. Okay, so we're going to look at some of his conclusions. So let's look at some of the conclusions of the special relativity. Conclusions of the special theory of relativity. Special theory of relativity. Number one, from this theory, Einstein concluded that energy and mass are equivalent and interchangeable. So the first conclusion was energy and mass are equivalent and interchangeable. So you can convert mass to energy or energy to mass. And the formula relating energy and mass was, I think everybody knows this formula, mass times the speed of light squared. This is the formula relating energy and mass. So if you're able to convert a certain amount of mass to energy completely or to radiation, then this is the amount of energy you would get. So in this formula, M stands for mass, C is speed of light, which is 3 times 10 to the power of 8 meters per second, and E is the energy obtained when the mass is converted to radiation completely. When the mass is converted to energy or radiation completely, converted to radiation completely. Okay, so this is Einstein's famous formula, that mass is a form of energy. You can convert mass completely to energy. You can also convert energy to mass. All right, so let's look at an example. Calculate the amount of energy can be obtained if 1 gram of a substance is converted to energy completely. If a substance is converted to energy completely. Okay, so the mass is 1 gram or 10 to the power of -3 kilograms. Okay, so we're looking for the energy. The energy is mass times the speed of light squared, so that will be 10 to the power -3 times 3 times 10 to the power of 8 squared. Okay, so you've got, this is 9 times 10 to the power of, you got 16 minus 3, 13 joules. This is the amount of energy you get, which is enormous amount of energy. Okay, and the second conclusion he came up was, as speed increases, length decreases. Okay, let's say L naught is length measured with respect of a device which is at rest with respect to the object which is being measured. Okay, and let's say L is length measured with respect to a device which is moving with a speed v with respect to the object whose length is being measured. Okay, then we have the following relationship. The length measured with respect to the length measured by a device moving with respect to a device moving speed v is given by the product of the length measured with respect to a device at rest with respect to the object times this one minus v over c squared. Okay, so this is length measured by a device which is at rest with respect to the object whose length is being measured. This is length measured by a device which is moving with the speed v with respect to the object that's being measured. Then these two are related by the following formula. Okay, example. Let's say the speed of an object as measured by a device at rest with respect to the object, let's say is 1 meters. Calculate its length with respect to a device which is moving with the speed of 1% of the speed of light with respect to the object. Okay, so the length as measured with respect to a device at respect to object is 1 meter, so that's L naught. L naught is 1 meters, and the device is moving with a speed v. V is 0.1% of the speed of light. Okay, which means 0.01 times the speed of light. Okay, that's 1% of the speed of light. So the question is to find the length as measured by the device moving with the speed v, with this speed with respect to the device. So we have L equals L naught square root of 1 minus v over c squared. Okay, this of course implies v over c equals 0.01. Okay, so this one is square root of 1 plus, well, 10 to the power negative 2 squared, or square root of 1 10 to the power of negative 4, or 0, 0, 1. Okay, so this would be, there is 1 over here. The speed, the length is measured with respect to the device moving the speed of 1% the speed of light. So it's very small change but different. All right, and the third conclusion was, as speed increases, time decreases, or sometimes called dilates. Okay, so in this case also let I'll say T naught, let T naught be time measured with respect to a device that is at rest with respect to the event. Time measure, or say on the other side. Let T naught be time measured by a device at rest with respect to the event whose time is being measured. Okay, and let's say T be time measured by a device that is moving with a speed v with respect to the event. Okay, then these two time intervals are related by the following formula: T equals T naught square root of 1 minus v over c squared. Okay, so as you can see, as this ratio will be smaller than the initial time interval, so the time decreases as the speed increases. Okay, example. Let's say time measured with respect to a device or watch at rest with respect to the event is, let's say, 10 seconds. Calculate the time measured by a device moving with the speed of, let's say, half the speed of light, half the speed of light with respect to the event, Okay, so we have it, the time measured by a device at rest with respect to the event is T naught, that's 10 seconds, and the speed by which the other device is moving with respect to the event is half the speed of light, or 0.5 c. Okay, that implies v over c is 0.5, or half. So we have to calculate t, the time measured with respect to this device that's moving with the speed of half the speed of light. Okay, So t equals t naught square root of 1 minus b over c squared, and that is 10 seconds, and then we've got 1 minus 1/2 squared. That's 1 minus 1/4, so that's 10 times square root of 3/4 seconds, or 5 square root over 3 seconds, right? And the fourth conclusion is that before, as speed increases, mass increases. Okay, so let's say m naught is mass measured with respect to a device at rest with respect to the object. No, let's say measured by a device at rest with respect to the object. Okay, and let's say m is mass measured by a device moving with a speed v with respect to the object. Okay, then we have the following relationship: mass equals m naught square root of 1 minus b over c squared. Okay, all right, so these are some of the conclusions Einstein came up by developing the special theory of relativity based on Michelson-Morley experiment. As you can see, some of these conclusions contradict common sense, but they have been proved experimentally. Okay, now we're going to look at the second experiment, the black body radiation experiment. The black body radiation experiment. We have already discussed this experiment, but let me go through it again. Okay, now when an object is heated, it emits all kinds of radiations. It emits radiations with different kinds of wavelengths, and an experiment was done to study the distribution of the intensity of the radiation as a function of wavelengths. Okay, that's what we call the black body radiation experiment. Okay. So when an object is heated, it emits radiation of all kinds of wavelengths, wavelengths. That's electromagnetic waves. Okay, so in the black body radiation experiment, a study of the intensity distribution of the wavelengths as a function, a distribution of the intensity of the radiation as a function of wavelengths was done in the black body radiation experiment. In the black body radiation experiment, a study of the distribution of intensity, of the intensity of the radiation emitted as a function of wavelength was done, as a function of wavelengths was done. Okay, and this is the following, this is the result they obtained. Okay, so let's say this axis is the wavelength lambda, and this is the intensity corresponding to each wavelength, and they got a curve that looks something like this, that is, the intensity of low wavelength radiation was very, very low, and then reached a certain maximum over here, and then decreases, the intensity decreases for very, very large wavelengths. So an attempt was made to explain this experiment using classical physics. Okay, they're able to explain this side over here, okay, but it continued like this, and they're able to explain this side over here, but also this one continued like this. They were never able to explain this turning point over here. Okay, so classical physics failed to explain this experiment. Classical physics failed to explain this experiment. But a scientist by the name Max Planck was able to explain this experiment using two postulates. A German scientist by the name Max Planck was able to explain this experiment, using the following two postulates. Able to explain this experiment using the following two postulates. Now, these postulates were, the first one is light is propagated in the form of particles called photons. So his first postulate was light is propagated in the form of particles called photons. Remember, the wave nature of light has been established firmly from Maxwell's equations at this time, but Maxwell has to use a particle property of light to explain this experiment. Okay, he's assuming that light is propagated in the form of particles and not waves. All right, and the second postulate he used was the energy of a photon is proportional to its frequency. Energy of a photon is proportional to its frequency. Okay, so let's say if E stands for energy of one photon, and F is its frequency, then this postulate states that E is proportional to the frequency, or the ratio between energy and frequency is a constant. Okay, and by fitting his the curve, he was able to calculate this constant, and the value of this constant he came up with was 6.6 times 10 to the power of negative 34. This is called Planck's constant, and is usually denoted by H, So we have E over F equals H, or customarily written as the energy of photon is called Planck's constant times its frequency. Okay, so these are the two postulates that enabled Max Planck to explain the black body radiation experiment. All right, and if there are n photons, you just multiply by n. For n photons, then you've got En equals NHF. Okay, so you see this one has both the wave property and particle property of waves. You see n is particle property, we're counting particles, but frequency is also wave property. So this formula is a representation of the particle and wave property of light. The current understanding of light is that it's both a wave and a particle. So this represents the particle property of light, this n, because you can count wave, but you can count particles. And frequency is property of waves. So this formula represents both particle and wave properties of light. All right. But at the time, people thought that this was just mathematical trick. People didn't take him seriously. But then another experiment was done based on these postulates that convinced scientists of the usefulness of these postulates. And that experiment was the photoelectric experiment. So let's look at the photoelectric experiment. Now, photoelectric experiment refers to the removal of electrons from the surface by light. If you bombard a surface with a light, electrons will be ejected from the surface. Okay, so this photoelectric experiment refers to the removal of electrons from the surface by light. So photoelectric experiment refers to the emission of electrons from the surface of a metal when the metal is exposed to light, or radiation is exposed to light. Okay, so when light hits the surface, then some of the electrons will be removed from the surface. That's what we call the photoelectric effect. Okay, now let's see why this experiment contradicted classical physics. Okay, now classical physics assumes that the greater the intensity of the light used, the greater the kinetic energy of the emitted electrons. Okay, classical physics predicts that the greater the intensity of the light used, the greater the kinetic energy of the electrons emitted. Okay, so classical physics predicted that the greater the intensity of the light, the greater the intensity of the light, the greater the kinetic energy of the emitted electrons, the greater the kinetic energy of the emitted electrons. But the problem was, this experiment found out that the energy of the emitted electrons is independent of the intensity. But this experiment found out that the kinetic energy of the electrons does not depend on the intensity of the electrons. Electrons does not depend on the intensity on the intensity, but on the frequency of the light, on the frequency of the light. Okay, so that was a contradiction with classical physics. Classical physics predicted that the energy of these emitted electrons will depend on the intensity of the light used. But this experiment found out that the energy of these electrons does not depend on the intensity of the light, but on the frequency of the light. That means, let's say violet has higher frequency than red light. So if you use a very faint violet light and a very intense red light, the energy emitted by the violet light actually will be stronger than the energy emitted by the red light. So, since classical theory failed, an explanation has to be developed for this experiment, and the scientist that explained this experiment was Albert Einstein. Einstein explained this experiment using Max Planck's postulates. He was able to explain this experiment using Planck's postulates. Okay, basically what Einstein said was when this electron is bombarded by high intensity light, let's say, but now according to Planck, high intensity means basically a lot of photons. Okay, even though this surface is being bombarded by a lot of photons, it's only one photon that's going to bombard one electron. Okay, it doesn't matter how many photons there are. Chances are that this electron will be removed from the surface only by one photon. So it doesn't depend on how many photons you have or how intense the radiation is. It just depends on the energy of one photon. And the energy of one photon, according to Planck, depends on frequency. So that's why the energy of this emitted electron depends on the frequency. Okay? So Einstein is using Planck's postulates to explain this experiment. First, the intensity is related to the number of photons according to Planck's postulate. Okay, high intensity means a lot of photons. Now, it's very unlikely this electron will be removed by more than one photons at a time. It's very likely that this electron over here is bombarded by one photon only. So it doesn't matter how many photons you have, this electron will be emitted only by one photon. So that's why it doesn't depend on the frequency, on the intensity. Even though you have a lot of photons, it's only one photon that's going to collide with the electron and remove it. And the energy from photon is proportional to frequency according to Planck. So it follows that the energy of the emitted electron depends only on frequency. Einstein said the electron will be removed only by one photon, irrespective of the number of photons or intensity, irrespective of the number of photons, which is basically intensity. Okay, it can collide only with one photon at a particular time. Okay, respect the number of photons. This is intensity. And since the energy of photon is proportional to frequency, the energy of the of the photon of the emitted electron should be proportional to frequency. And since the energy of a photon is proportional to frequency, it follows that the energy of the emitted electrons should be proportional to frequency. The energy of the emitted electrons should be proportional to frequency. Should be proportional to frequency. So that's how I explained it. Okay? It doesn't matter how many photons you have or how intense the light is, the electron is going to be bombarded by one photon. So the energy of the emitted electron depends only on the energy of one photon, and the energy of one photon is proportional to the frequency of the photon or of the light. So it follows that the energy of the emitted electrons is proportional to frequency. So that's how Albert Einstein was able to explain this experiment. Even though Albert Einstein has done a lot of things, it's for this explanation that he won the Nobel Prize. Okay, so before we express Einstein's equation mathematically, let's define what you call the work function. Work function. We're going to use W to be presented, capital W. This is the least amount of energy required to remove an electron from the surface of a metal. This is the energy required to remove the most loosely held electron from the surface. In other words, this is the least amount of energy needed to remove an electron from a surface. Okay, so let's say I have this metallic surface over here. You got light coming over here. You know, there are a bunch of electrons over here. The most loosely held electron will have the largest kinetic energy because it requires only very little energy to remove it. But the other electrons which require more energy to remove, they're going to have less kinetic energy when they come out. Okay, so the electron, the most loosely held electron, will have the maximum kinetic energy once emitted from the surface. Okay, so you got this energy coming, the energy of photon, which is Planck's constant times frequency. Okay, some of it will be used to remove the most loosely held electron, which is the work function, and then the remaining will be converted to kinetic energy of the emitted electrons. But since we're looking at the most loosely held electron, this would be the maximum kinetic energy. Okay, so this is Einstein's formula. Okay, you got a photon of this energy bombarding an electron from the surface, or knocking out an electron from the surface. Now this equation applies to the most loosely held electron. Okay, so by definition, the energy required to remove the most loosely held electron is work function, and then the remaining energy is converted into kinetic energy of the electron. And since the most loosely held, this energy would be the maximum possible kinetic energy of the electrons emitted from the surface. Okay, so this is basically Einstein's equation. Okay, so Ke max, this one, is maximum kinetic energy of the emitted electrons. Kinetic energy of the emitted electrons. You can have different kinds of kinetic energy of the particles, but in this formula we're looking for the maximum kinetic energy, that is the energy of the most loosely held electron on the surface. All right, so let's look at an example. Let's say the work function of a certain metallic surface, let's say, is 2 electron volts. Okay, calculate the maximum kinetic energy of the emitted electrons when the metallic surface is exposed to violet light whose wavelength is 400 nanometer. Okay, so we have this surface is being bombarded by a violet light, and then of course electrons will be emitted from the surface. So we're looking for the maximum kinetic energy. If we can get the maximum kinetic energy, we have to deal with the most loosely held electron. So the energy required to remove the electron from the surface for the most loosely held electron is 2 electron volts. Okay, so let's write the given values. We have the work function 2 electron volt, but 1 electron volt is 1.6 times 10 to the power of negative 19 joules. Okay, so the work function is 3.2 times 10 to the power of negative 19 joules. All right, and we're given the wavelengths of the light, which is 400 times 10 to the power of negative 9 meters, or 4 times 10 to the power of negative 7 meters. All right, and we want to calculate the kinetic energy maximum. Okay, so we're going to use Einstein's formula. You've got HF, the photon hitting the surface, then you've got the work function, that's the least amount of energy needed to remove an electron, and then you've got the maximum kinetic energy of the emitted electrons. Okay, so the maximum energy of the emitted electrons is HF minus the work function, but we don't have frequency, we have wavelengths, so we're going to replace frequency by C over wavelengths. Okay, minus work function. All right, so this is Planck's constant is 6.6 times 10 to the power of negative 34. The speed of light is 3 times 10 to the power of 8, and our wavelength is 4 times 10 to the power of negative 7 minus the work function, which is 3.2 times 10 to the power of negative 19 joules. Okay, so we have from the numbers 6.6 times 3 divided by 4, and from the powers we have negative 3 plus 8 is this is negative 34. Negative 34 plus 8 is negative 26, and negative 26 plus 7 is 9, 10 to the power negative 9, 19, I mean, negative 19. So this is minus 3.2 times 10 to the power of negative 19. Okay, so this looks like 3.3 times 3, 10. It might be about 5, I would say. This is approximately about 5 times 10 to the power of negative 19 minus 3.2 times 10 to the power of negative 19. that is 1.8 times 10 to the negative 19 joules. Okay, so that's the energy of the emitted electrons, the maximum energy of the emitted electrons. All right, so just to review, you got a photon whose frequency is Planck constant times the frequency. Some of the energy would be used to remove the electron from the surface, and then the remaining would be the energy of the emitted electrons. But since we're dealing with the most loosely held electron, then this would be the maximum kinetic energy. All right. Next, we're going to look at de Broglie's hypothesis. De Broglie's hypothesis. Now, from Max Planck, what we learned is that waves have particle properties. Okay, according to Max Planck, light is propagated in the form of particles, right? So de Broglie hypothesized that if waves have particle properties, then particles also should have wave properties. De Broglie is a French scientist, stated that if waves have particle properties, then particles should also have wave properties. Should also have wave properties. Okay. And so to obtain the wavelengths of particles, he used the following questions. One is, we've got energy equals mc squared. So replace it c by the speed of the electron. This is the speed of the electron. Okay. So from this, he replaced the energy of the electron by E equals mv squared. And then from the formula, E equals h times frequency, which is hc divided by the wavelengths. Replaced c by v, which is speed of the electron, and he got h speed divided by the lambda, where v is speed of the electron. So he equated these two quantities, is mv squared equals this one, h speed divided by the wavelengths. Okay. So let's try to obtain a formula for the, so one speed goes away, you've got mv equals h over lambda, and then this of course implies lambda equals h divided by mv. So this is the formula he came up with. Okay, so lambda is the wavelengths of a particle moving with a speed v. Okay, this one doesn't have to be an electron, it can be any particle. So let me say particle over here. Okay, this applies for any particle. So that's a formula for the wavelengths that de Broglie came up with. Okay, so example, let's say calculate the wavelengths of an electron, let's say moving with a speed of, let's say, 2 times 10 to the power of 6 meters per second. Okay, so the mass of an electron is about, I think, 9.1 times 10 to the power of negative 31 kilograms, the mass of the electron. So, and we're told the speed is 2 times 10 to the power of 6 meters per second. And we're looking for the wavelengths, question mark. The wavelength is h divided by mass times speed. So that is 6.6 times 10 to the power of negative 34 divided by, we've got 9.1 times 10 to the power of negative 31. And then the speed is 2 times 10 to the power of 6. Okay. All right. And the two scientists by the name de Viesen and Germer were able to show that electrons actually have wave properties. And two scientists by the name de Viesen and Germer, were able to prove experimentally that electrons have wave properties and proved that the de Broglie hypothesis was correct.